is Emre Sertöz from Leibniz University of Hanover, which is going to talk about computing linear relations between one-periods.
All right. Well, first, thank you for the invitation to be here, Hossein, and well, all the organizers. And well, it was a pleasure to be here, both inside the classroom and outside the classroom. But I must start with the ritualistic apologies. One of them is I planned my talk to be slightly expository, so that Hossein gave me license to do this. So I hope it will be kind of elementary most of the time. But I will get to something that we are doing. And to give a hint as to what we mean by computing linear relations, I will talk about a little bit of the affiliation of my collaborators. So Joaquin is from a director at Max Planck Institute for Software Systems. And James Worrell is professor in computer science department. What we really want, so when we say compute, we mean really compute. So I will get to the meaning of that. So they have some applications to discrete dynamical systems and one-periods. But today we will talk about just the one-period side of this. Since we will be computing linear relations for one-periods, I guess where I should start is with the definition of these objects. So first, the proper definition is slightly long, elementary but slightly long, so I'll write the slogan. The slogan should be univariate, or I should say integrals of univariate algebraic functions. I didn't close the bracket yet. Univariate means single variable. And I would like everything inside to be defined over Q bar. All right, so before I define what this thing is properly, let's start with examples. For instance, log 2 is a univariate integral from 1 to 2 of dx over x. And you see the endpoints are algebraic numbers. I have a univariate, even rational function, let alone an algebraic function. And so this is a one period. And in fact, you can see that log alpha for alpha algebraic is a one period. Algebraic numbers themselves are one periods. Integrate dx from 0 to alpha, right? Let's do something slightly more interesting. Pi, for example. So I have three different representations for this, and there are many more that you could take. One of them, let's take dx over x again. And in the complex plane, I integrate over the unit circle. So that's, and I can multiply, well, I can multiply here by 1 over 2i. So that's fine. And here's another one. This is now hints at the algebraic function part. So now I integrate the square root of 1 minus x squared. And I'm essentially computing the area of a circle. So this one, I think I want to do this times 2 minus 1, 2. Put 2 here. And so on. I mean, you can keep going. And this is an important feature of these things. There are typically many different integral representations for a single number. Right? So this you should keep in mind. This is going to cause a problem.
In the first formula, you didn't have a Q bar function.
Say it again?
In the first formula, you didn't have a Q bar function. Just go and move things over Q bar.
This is Q bar to me. What did you like? Ah, yes, good point. No, this is fine. You know, the domain of integration is kind of flexible.
Okay.
Yeah, so I could have made it like rectilinear or something. It doesn't matter. All right, one more. So the usual integrals over some domain. So probably you see now, this is of course the kind of integrals people wanted to study a long time ago, and they invented Riemann surfaces and hence algebraic curves from these things, and we will go through the same procedure soon. So basically periods of elliptic curves, and even you can have incomplete integrals, so where the path is not closed, that's also fine. But we would want the endpoints of gamma to lie in here, minus the poles. And this answers the point that you raised. Since the paths are usually flimsy and you can move them around, what's important here is that the endpoints, which you cannot move without changing the value of the integral, the endpoints should be defined over q bar. OK, now we can get to the proper definition. So my integrand, my one form, will be of this form. So there's an algebraic function times dx. So this is so we take a path with endpoints in q bar minus the poles of omega. But here, so I'm kind of being sloppy in the kind of 18th century way. I want to integrate omega over this path in a moment. That usually involves choosing a branch. You need to choose the branch for omega over this path. For example, here, that was kind of implicit. I chose the positive branch for 1 minus x squared. Well, usually choosing that branch really means you have a path in the Riemann surface associated to this differential. So let me write, I'll get to this in just a second. All right, so what we'll call is the value of the integral of omega over gamma. This, let's call it elementary one period. So it's elementary because I can write it as the value of a single integral. And we will allow ourselves q bar span, linear q bar span of these things, and they will be 1 periods. So linear q bar span of these things are, by definition, 1 periods. All right. Now here, there's something to think about a little bit. So there's this value that's typically going to be transcendental. I mean, here you can see we are going to get numbers like pi. So the value itself is kind of complicated. But the representation for that number that I've given through the integral is a little bit simpler. So omega itself is essentially an algebraic function. That's easy to represent. Gamma is flimsy, really, the endpoints matter. So that's simple. I mean, you can write down a rectilinear path in C, so just by straight lines. So that would be simple to represent. So let's make that, no, so we need to distinguish between a complicated, I mean, a number which has no hold in it versus the representation. So we distinguish between this value and maybe the pair or the representation which is essentially this pair. But since we cannot really touch these numbers without the representation, every time I write down an integral, I really mean we have a grasp on these two things, this pair. And this is called an integral representation. All right. So here's this warning that I made already here. So let me write this down and make it official. So given two representations, possibly of the same number, it's hard to decide whether or not they really represent the same number. So given these two representations, it is hard if these two integrals are the same. Now, if they're different, you can numerically approximate and you'll figure it out eventually. But if they're the same and you're numerically approximating, they seem the same, and you don't know when you should stop and do something else. Yeah, so this is what's the difficulty. One of the implications of the result I'll say today is that you can now decide equality and much more besides. But I should say that, in fact, this sort of deciding equality is open, widely open in higher dimensional integrals. In higher dimensional integrals, truly equal. So it's also unclear whether or not there exists even a method to decide equality in higher dimensions. And this is Concept-Laguerre conjecture would, in fact, imply that there exists an equality modulo some details. So they say their conjecture wouldn't, but in fact it does a little. Okay. So now let's get to relations. So this is theorem in progress. Hence, I call this talk more of an expository talk. But I think I have high confidence that we're going to pull this off. By next year, let's say. So there is an algorithm which takes the integral representation of finitely many let's say elementary 1 periods. I mean, this part really doesn't matter. And outputs the Q-bar vectors, well, let's say outputs the basis, which is a basis for the Q-bar space of relations. So here when I mean by relations, I mean, of course, vectors in Q bar to some power. So you've given me integral representations of k periods, alpha 1 through alpha k. The space of relations are these tuples, k bar tuples. such that the sum is 0. Right? So there's a q-bar vector space in here, and it has a basis. So I would like to be able to compute the spaces. And maybe here's what, for this, here's an example of what the answer would look like. Not the algorithm, but what the answer looks like. So let's say alpha 1. This is a particularly simple example that I think a computer can do today. But in general, no computer can do this. So not in this generality at all. Okay, so we established that log 2 and log pi are 1 periods. I gave their integral representation here. Alpha 1, let's say, is this integral. Note, however, why this is a simple example is that the Riemann surface associated to these objects, I'll get to this Riemann surface in just a second. In all three cases, it's just a P1. P1 perhaps with punctures, whatever, but it's a P1. And it's just relatively simple. It's kind of a classical case. And the relations between these is just, there's one relation between them, and it's this one. So it's spanned by a single vector. And that's what this algorithm should do. Yeah, so you give these 3 integral representations, 2 over there and 1 over here, and you should get this vector as output, for instance, or a multiple of it. So while I raise the board, let me say that, of course, there's a distinction between theoretical algorithms, which says if you have infinite time and your computer has infinite memory, then the algorithm would actually work. So that's one kind of algorithm. And to have rigor right now, that's the kind of algorithm we will give. But then there's also another algorithm, which is practical. So it actually gives the result to you, but you will not know until the computation ends that the computation will certainly end, unless you assume like Mumford-Tate conjecture or something. So there are 2 algorithms, one practical but might not terminate. But if it terminates, you know you have the right answer. And then another algorithm that's rigorous, but no one will experience that algorithm ever. So I should say this kind of result has some implications. I will write 2. So first of all, regarding transcendence. So if you give me alpha at 1 period, then I can decide if alpha is transcendental or not. I ask if the relations between, if there are any q-bar relations between 1 and alpha. Yeah, so this is 0 precisely when alpha is transcendental. So you get an algorithm to decide transcendence of 1 periods. The other one is deciding equality. So, sorry? Sorry, this is 0 and alpha is transcendental. No, alpha, what do you mean? Alpha is not equal to a q-bar multiple of 1. So alpha is not q in q1, q-bar. There is no, so there are no relations between 1 and alpha. Yes? Is this okay? Did I make a typo? It's hard to see on the board sometimes. So equality. Yeah, so you give me 2 integral representations, so that's maybe these are 1 periods. So 1 minus 1 is in the vector space of relations. Phenomena. And so this was the problem that I mentioned over here, that in general it's hard to decide this equality. And of course, this adjective is still true. I mean, even with this algorithm is not so easy to, it takes a while to run through it, yes. Yes. Well, I give you all the relations. So in particular, you decide, I give you a basis for the space of relations. So if I give you 0 and I say this is a basis for the space of relations, then you know there are no relations.
Is it theoretically against the algorithm?
No, I give you 2 algorithms. I should say the core of the algorithm is due to someone else. Wait just a second. A bad time to lose my voice. So, what were you saying, Hussein? I was saying that there are 2 algorithms, really. So the first algorithm, so no one will ever implement this algorithm. It's insane. But we will be able to prove that this algorithm terminates and gives the right answer. And then there's a second algorithm, which actually works. So this is actually not, I'll tell you. So the second algorithm, if it terminates, you know you have the right answer. But to guarantee termination before it ends, to guarantee that this method actually is an algorithm, it terminates, you need heavy conjectures. Sure. Yes, sure. Well, really, honestly, the hardest thing is finding the dimension. Yes, yes. One more. This is the other fact is effectivity. These are trivial consequences of this result, but the statements, some of these things are important. Effectivity, for example, it says the Q-bar vector space of 1 periods is effective. This just means you can, essentially it boils down to being able to check equalities. You can do calculations in this Q-bar vector space. Now, this version is not so impressive. The version that no one has would say the ring of periods, so involving integrals of higher dimensions, is effective, right? So that's an enormous, that would have been an enormous result. All right. So this algorithm, currently it's in the form of a desire, but almost certainly doable. But so even wanting something like this would have been completely unreasonable in 5 years ago. So something like this, let me write this down. So what happened? So really, it's not that we happened. It's actually 2 results that are completely independent of us. The most important is the result due to Huber and Stolz. So they have a monograph on 1 periods, and they essentially close the subject. So what they say is that they give so in their own words, they give a qualitative description of all relations between 1 periods. All right. So this is kind of like the, a little bit like the Kontsevich-Zagier conjecture for periods. So they prove it for one period. And I can tell a few words, and I will actually, most of my talk will be about the result. So I will expand on this statement. So this says, so Deligne introduced one motives, and he introduced essentially functors to mixed Hodge structures, and therefore introduced their periods. So they say that, okay, this category of one motives is an abelian category. Whenever you have a relation, it's because in this category of one motive something splits. Now I will make this more precise, but let me say, I mean, they close a chapter on transcendental number theory, which so okay. So Lindemann, Schneider, Baker, and others. This is on the transcendental number theory side, and motivically, Grothendieck, Kontsevich, Zagier. So, of course, many others. So we were discussing, I think, Matthew's principle. Famous people get all the credit. And this is what happens here. But this is by itself is not enough because, of course, I mean, you have a category of one motifs. Some splitting gives you relations. You have to be able to do this in practice. And in fact, all the splitting conditions are, again, really transcendental relations. I mean, again, it just boils to being able to check transcendental identities. Well, it depends on how much you know this result. I mean, not you particularly, your taste, because to me, it's quite a bit more. But people who are experts on the subjects say, well, okay, it's an improvement on this. But I mean, they wrote a whole monograph because, yes, the engine behind this is Hustholz's analytic subgroup theorem. But you have to add a ton of bells and whistles to it. And so it just gets a little bit more complicated, but the true depth is just Hustholz's analytic subgroup theorem, yes. Yes, so the old result is if you have integrals where you have closed loops here. Yeah, so your paths are closed. So that actually is just, can be deduced from Hustholz's analytic subgroup theorem. And with these open ends, and with not holomorphic differentials, but possibly differentials with poles, so that these two, and especially the combination of both, it makes the theory a little bit more complicated. Okay, two. So we need one more thing to make it a little bit more practical. And that's the second part. In fact, I believe I heard a couple of lectures ago being discussed at the back that this was impossible, but this has been done recently. So an algorithm to compute the endomorphism ring of an, well, let's say, of an abelian variety. But the practical one is for Jacobians of curves. So this algorithm, well, it's a lot of people, but it's recent. So Lombardo gives you slightly more theoretical algorithm. It handles all cases. And then the practical one, so Costa, Mascot, Seisling, void. So this is 2020. And completing the practicality, let's say, is Brown, Seisling. So what really happens here is that finding endomorphism rings really boils down to computing certain relations between periods of curves. Well, that's sort of what we were trying to do. So these guys help you compute rapidly periods of curves and guess relations between them. And they give you ways to prove that you've found all relations. So this is about computing like the dimension. So these two are related because here, maybe I add it here. So one motives are generalizations of abelian varieties. And I do hope to come to this definition. And this is essentially the most transcendental part of the data. The rest of the transcendence, we think we can handle. Yeah, so algorithm combines these two things. So this is, the relation is a little bit like Wüst-Stolz's analytic subgroup theorem, which tells you a geometric source of all relations, relations between closed periods. So where you have a closed path here and a homomorphic form here. And the new result of Huber and Wüst-Stolz, which handles all integrals, all one-dimensional integrals. So you have to do a lot of sort of fiddling around to get from one thing to the other. Okay, so now let's flesh out what's behind these things. So from numbers, we need to get to curves, and then what these guys call one motives. Any questions so far? All right, so first of all, let's approach the subject of one motives in a pedestrian way. Now, someone has given us an algebraic differential. To this, I'm going to associate a curve, right? The first piece of my geometric data. So I'm going to write this as fx dx, where fx satisfies a polynomial that's called pxy in two variables with q-bar coefficients in x and y. So f of, oops, so that means p of x of f of x is 0. I mean, that's just what it means to be algebraic function. And so I want an irreducible p. The curve defined by p, the projective closure of the affine curve defined by p is geometrically integral. Of course, it's going to be singular in general, but this we don't care. We are going to normalize it. Before we go on, let's just do an example. I think I wrote down this integral. Okay, let's just take 2 out now. So here, f is this square root. And you can see then p of xy ought to be y squared minus 1 minus x squared. Yeah, so y would be the square root of 1 minus x squared. Writing this gives me the equation of the unit circle, although we're thinking of the complex numbers. And then the curve C bar, the projective closure, is cut out by the homogeneous equation, like so. Of course, this is a quadric, so it's a conic in P2. It's isomorphic to P1. P1 has no interesting 1 periods. So we're not done yet. Yeah, so I lost my differential. So there are no 1 differentials here that would give me interesting periods. So let's continue. So this, as they call that, let's put a tap on this and continue with our construction. So I have my omega. Our omega is a rational differential on the smooth curve C, which is the normalization of C. Right, so I have C bar. In principle, you blow up the singularities until you get something smooth. That's C, or that's the normalization equivalently. And omega is a rational form. So I need to deal with the poles. So I'm going to take a curve C0, which is going to be C minus the poles of omega. So that's the reason we do this. Omega becomes a holomorphic form on C0. So my cohomology will certainly see it. This was not mandatory, but it does make it standard. So of course there are differentials of the second type, which would appear in first cohomology, but this handles any kind of differential. All right, and so we were talking about a path gamma, but really any one chain with endpoints. Let's call this D, endpoints of the chain. And the endpoints of the chain should lie in algebraic points of my curve and on this curve minus poles. I don't want to hit the poles of my differential because I don't want to deal with divergences. So if I take a path, define the endpoints, then I can view gamma as a homology class in C0 relative to D. So here I can also view omega as a cohomology class, in fact, in the holomorphic part. All right, so the upshot of this is that the integral is a period of the mixed Hodge structure So the reason you want to do this, of course, is that curves are still relatively fragile. Just like algebraic varieties, you can't really form quotients as you want. They don't have the right subobjects. But you pass to mixed Hodge structures, you can talk about quotients. By the way, for a period of a mixed Hodge structure, I mean there's either a Z lattice or a Q vector space corresponding to Betti cycles, and I have forms, Q-bar forms, giving me the Hodge filtration. So pairing of these two things gives me numbers. Those are periods of a mixed Hodge structure. All right. So let's say what happens. So all elementary periods periods arise as periods of mixed Hodge structures of weight 1. And the converse is almost true. So the converse, you can also say which kind of mixed Hodge structures you need to consider so that you get actually 1 periods coming from curves. So you need polarizable and with the appropriate weights. I won't write this down. All right, so now we're close enough to state the theorem of Huber and Wüstholz. So let's take alpha 1 through alpha k be 1 periods. And let Ci, Di be the pairs as above or sideways, I mean as in here. So given omega and gamma, I constructed a curve, possibly affine but smooth. So this is smooth curve, not necessarily projective. And Di is just a bunch of rational algebraic points. You construct those pairs as I just did here. And then here's the main statement of Huber and Wüstholz. The relations, I should say all the relations between alpha i's arise from the quotients of the mixed Hodge structure Okay. So each of these curves gives me a mixed Hodge structure. I take the direct sum. This thing possibly has many quotients in the category of mixed Hodge structures. All of those quotients give rise to various zero pairings. So I will explain this in a second. But that's the crux of the result. When you want to find relations between alpha i's, you construct a comparatively large object with now many, many, many periods. And then you actually end up finding all relations between all these periods. And then from them, you just read the ones that relate to your alpha i's. All right, any questions while I raise these two boards? Well, so there's a lot behind the scenes. I mean, these endomorphisms, the way I've stated it was because these are familiar. I haven't talked about one motives yet. You can translate this to the language of one motives, and then it gives you, for example, endomorphisms of Jacobians. Endomorphisms of Jacobians relate to correspondences between curves. So there are, of course, algebraic geometric phenomena behind the scenes. I should give you the motivating ideas to what happens. Or maybe So there are two directions. The hard direction, as was mentioned, is actually related to Stolz's analytic subgroup theorem. I'll do the easy direction. So if you have a quotient, what happens? So take, I mean, we could have taken something harder, but take an elliptic curve. And consider the short exact sequence, which is this stupid short exact sequence. I'm going to take E cross E. So if I take cohomologies, E cross E is going to, I will use it to give H1 plus H1. And I just take projections. I have some choices, but it doesn't matter. I just pick one like this. I'm thinking of projecting onto the second factor here and including the first factor to the identity using the group structure. So this whole thing, when you compose, let's say, goes to the 0 point. So the reason for this example is that you see now what kind of relations will occur. If I take a form on H1, so I'm thinking over here, and gamma in the Betty of E, then I can cook up a stupid 0 here, and I obtain it like this. First, I include gamma from this E into one of the fibers over here, and I pull back a differential form, the differential form over here. What you can do now is, my base change, I could have written it as so. But now the composition here sends everything to a point. So the image of gamma is just a point. And I'm integrating here one form. Of course, if you integrate one form over a point, you get 0. Now this tautological 0 could have been hidden from me. So I could have chosen a bunch of bases for H1 over here. I could have chosen some basis of differentials. Then it's not clear what is a pullback and what is a push forward. But of course, whenever my combination of loops and forms are of this form, they must pair to 0. And the crux of the theorem is that whenever you have a 0 of periods, it has just arisen from such a stupid construction. Can you say it again?
At the very beginning of everything, you fix an embedding of Q bar into C.
Oh, yes, yes.
You
Yes, fair point, fair point. No, I do fix, yeah. Huh? Yes, yes, yes. Yes, I have Q bar inside of C, yes, forevermore. I mean, it's just, I don't deal with these alternative embeddings. Okay, so in the last 5 minutes or so, I would like to talk about one motives now properly. So my goal in the previous section was to give the idea behind this, so slightly simplified. And the original definition is also not so bad. It's not like the original Wojcicki motives or something. It's fairly easy. I think the name is much more intimidating than the real thing. So first, we need a semi-abelian variety. is what's called a toric extension of an abelian variety. So what that looks like is, so let's say, so any semi-abelian variety surjects onto an abelian variety, and this is called, the kernel is the toric part, such that T is in fact just a copy of a bunch of GMs, or if you want, C stars. Yeah, so it's maybe I make a note here that the Jacobian of C0 for punctured smooth curve will always be a semi-abelian variety. That's why you want this to begin with. Now the second thing is a one motive is a complex where G is a semi-abelian variety, well, let's say defined over Q bar. L is just a free module of finite rank ZR. And phi is a group homomorphism to the algebraic Q bar points of G. So the objects are really basic in a sense. Morphisms, just very quickly, morphisms are morphisms of complexes up to isogeny. That means I can invert multiplication by an integer. Okay, so some theorems of these guys. So let's rephrase what they're doing. So first of all, the category of one motives coincides, or I should say, I guess, equivalent to the category what did I say here? So we previously wrote down this object. So this is a mixed Hodge structure coming from a curve, possibly punctured and relative. What I mean by generated is you can take direct sums, but also you can take subquotients. Yeah, so that's the important part. Essentially, the relations say that they come from subquotients. So I need to, what they did was find a category that captures all subquotients, and in a relatively geometric sense. So all subquotients now are going to be of this form, for a semi-abelian group and a bunch of points in that semi-abelian group. And of course, rephrasing that result, all relations between one periods, so I'll call that one period relations, arise from short exact sequences of one motives. So the example I did here was foreshadowing this result. E is an abelian group, and it's a one motive with trivial extension here and zero lattice here. So I can take the direct sum if you want. I take some projections. So I tell you what kind of zeros can occur if you have a short exact sequence. It's a slight generalization of what I did there. Okay. Okay, I guess I should have said, okay, say it again. Yes. But I allowed, I said a lot of things to give meaning to this word generated. So I allowed subquotients and direct sums. And all abelian varieties are quotients of Jacobians. Yeah. Okay. One more thing. So 2 observations I should say before I stop. So first one is so for abelian varieties, but with morphisms up to isogeny, all quotients or all exact sequences, short exact sequences, come from endomorphisms. Let me explain this statement. I mean that if I have short exact sequence of abelian varieties, I polarize and invert, I dualize to get this. And combining this splits A up to isogeny as B plus C. Well, what does this mean? This short exact sequence gives a map from A to B, but that's up to isogeny A again. Therefore, I have a map from A to A. And conversely, if I have a map from A to A, obviously I just compute the kernel and the quotient here with respect to the kernel. That gives me that gives me the short exact sequence. So computing short exact sequences of abelian varieties correspond to endomorphisms. Hence, the work I cited about computing endomorphism rings plays a crucial role here. So maybe I say in words that what needs to be done, given a one motive, such as this one here, I'm able to, other people are able to compute the endomorphism ring of A. So what you need to do is, whether given an endomorphism respects, first of all, this extension. So you need to be able to deal with toric extensions, and then you need to be able to deal with these morphisms coming from a lattice. So if you can deal with this, there's actually a surprising amount of transcendence here that you need to deal with. But if you can handle them, then you can realize which endomorphisms give you quotients of one motives. And from this, you can deduce all relations that you needed as coming from this theorem. Okay, I will stop here. Thank you very much.
Are there any